Okay, let's start. Okay, success criteria A, describe internal energy as an energy store. We have done this in kinetic model, right? We have done this in work energy power. That's made out of the total kinetic energy. And this is actually linked to the random motion of the particles. So for solid, they vibrate. And if temperature increase, they will have to vibrate faster. Okay, and the total potential energy between the particles in the system. Now, when two substances at different temperatures are in contact, the hotter substance will transfer thermal energy to the cooler substance. So it's always thermal energy from hot to cold, never cold to hot. That means I cannot pass cold energy to you. There's no such thing. It's always just thermal energy being transferred. And until they reach a state of thermal equilibrium. What is thermal equilibrium? When they are actually at the same temperature. We did this in a previous chapter at the same temperature and no net transfer. No more net transfer of thermal energy. And I emphasize the word net. Okay? So the hotter object will lose thermal energy, by right shouldn't be lose, will transfer thermal energy, and therefore its internal energy will drop. While the cooler object gets transferred, sorry, my grammar very bad, you all understand this, right? Gets thermal energy transferred to it. So, change of syllabus, we cannot say gain or lose thermal energy. Okay, transfer in, transfer out. Now, internal energy, therefore, is made out of the total KE and the total PE. Okay, so this is important. Internal energy, it is total KE plus the total PE. When it is heated, internal energy of the substance increases. When I heat something, what happens? I give you an example now to give you a glimpse of what is happening in this chapter. I have ice. What is the temperature of the ice? Oh, you are at 0? Can I have it at -10? Can, huh? Did I go through this with you already? Okay, very good. So if this is a temperature versus time graph and I heat up the piece of ice, I will have to start off with -10 degrees, right? So if I heat it up, what will happen to the ice? It will have thermal energy transferred to it, right? So will it melt or will it change temperature? Change temperature. So it will increase temperature until 0. Then what happens? Yes. Have you done this in Sec 2 somewhat? Done, So after that, if I continue to give it thermal energy, it will increase temperature again until 100 degrees, right? And then it will be stationary. Then if I continue heating it up, the temperature will increase. Yes. Not really. So it can be superheated. Okay. But of course that, like if you talk about the sun, what happens to those things around it? It will get very, very hot. So what is the actual temperature? I don't know. Maybe you can Google it. Okay. But what I'm here to tell you here is that over here, what changes? Temperature change. So the KE changes, right? Energy in the kinetic store changes. Any change in PE, any change in the potential store, no change. How about here? Any change in temperature? No change in temperature. So, but PE changes. Why? It's between the particles. Remember the rubber band? The further particles are apart from each other, the larger the potential energy. Okay, so PE change. So then I can extend this to other parts, and this is something that you need to know. That when I heat up something, not necessarily the KE will change. Not necessarily. Not necessarily the PE will change. But the internal energy, which is the sum of KE and PE, will change. Y'all got this? When I heat up something, what will definitely change? IE, KE, or PE? IE. And your IE depends on what is happening to the object. Is it gaining temperature? Is it increasing temperature? Yes. Then the energy in the kinetic store will increase. Okay? Is it changing state? When it's changing state, the temperature don't change, so the KE remains the same. But when it's changing state, the particles are moving either further apart or closer together. And therefore, the potential energy will change. Yes.
What's the difference between thermal and internal?
What is the difference? No difference. Because if you see in your work energy power, right, internal, then they bracket thermal. Okay, but try not to use heat energy. They don't mention heat energy. They only mention internal in your work energy power. Okay, so can I move on? Gas has the maximum internal energy. Okay, whether is it in terms of kinetic or whether in terms of potential, gas has the maximum. Therefore, solid has the minimum. The particles are very close together. Their potential energy is very low. The particles vibrate in their fixed position. They are not moving around, so their kinetic energy is the lowest. So in summary, gas has the maximum internal energy compared to the other two states. Heat capacity and specific heat capacity. Different bodies or objects have different capacities to store internal energy. Okay, by using the kinetic particle model, the capacity depends on the following. First is the number of particles. If I have more particles, definitely they will be able to store more internal energy, right? Then also by the nature and strength of the intermolecular forces. So what do I mean? For the same volume, solid and liquid tend to have larger heat capacities than gases. Okay, they try to use the spring, the force between particles. So this is in comparison to solid, liquid, gas. In between solid particles, they are held with very strong intermolecular forces. So when I give it thermal energy, okay, they cannot increase their temperature as fast because they have strong intermolecular forces. But compared to gas particles, they are not really pulled back by their fellow particles. So when I give it thermal energy, they'll just run. Correct? That you need to memorize heat capacity. It is a change of its internal energy per unit change in its temperature. Okay? So we use capital letter C. For caps, capital letter. What is Q? Q is thermal energy. What other names have we called energy by? What other symbols have we used? We use E, right? We use W, right? Which is work done, right? Yes. But now in thermal, he takes on a different name called Q. But it's still energy. Okay? Because this is another branch of physics already. We are talking about thermal physics. The previous branch we are doing Newtonian physics. But anyway, they are still energy. What is triangle theta? Triangle, have you all learned in math? Triangle means change. Theta means temperature. Change in temperature. So they use triangle theta. It is not the absolute temperature. It is the change in temperature. Okay? So let's look at the units. For energy, you all know it's joules, right? For change in temperature is either degrees Celsius or Kelvin. Have we talked about Kelvin before? Kelvin is by this guy, a British physicist. His name is Lord Kelvin. He's a lord, so he was conferred a title, okay, because of his scientific breakthrough or whatever. So they call this temperature Kelvin. So besides degree Celsius, we also have degree Fahrenheit. Yes, we also have Kelvin. But Fahrenheit not really in our syllabus. Okay, it's used by American. American uses the imperial units. For the British, they uses metric. Okay, so we follow British because last time we were under British. So Kelvin, please write this down. Please write this down. Change of 1 degree Celsius equals to change in 1 Kelvin. Okay? So what is 0, sorry, wait, 0 degrees? 0 degrees is 273 Kelvin. Exact what? Is that 273.15? But never mind. So 1 degree will be 274. So how much is okay? How much is 0 Kelvin? So we do not need to know this. We only need to know change of 1 degree is equal to change of 1 Kelvin. We only need to know that it is linearly related. Yes. That means change of 1 degree Celsius is change of 1 Kelvin. It is not equal to, take note, 1 degree Celsius is not 1 Kelvin. It is not. Only the change. And this chapter, we always deal with the change in temperature. The change, because like what we have done for the heating curve, we talk about changing temperature and all that, right? So we bear in mind, we always need to see the change in temperature. So far, are we okay? Now we go to specific heat capacity. Very good. To specific heat capacity, no caps, small letter. You need to memorize this. It is the change of its internal energy per unit mass for each unit change in its temperature. What is the thing that is now added? Per unit mass. Per unit mass. Okay? So the formula you need to memorize. It looks similar. Oh yes. Can I present the equation like that? Q equals to MC change in theta. Can but why didn't I do it? Because I hope by now you have known actually which way do I prefer? With fractions or without fractions? Yeah, I like my I like my equation as a one-liner, if you get what I mean. So, one line, no fractions. But why do I purposely present it this way? Because by now you would have known physics formula and physics definition, they are the same. The definition comes from the formula comes from the definition. Look at this thing that we are trying to define. We are trying to define specific capacity. It is equal to the energy per unit mass. Per means divide, right? Per means divide. So it is energy divided by mass for each unit change. Per unit change. That means per unit change in temperature. So the formula mirrors the definition. So it's like note 1. It is not useful to compare, not useful to compare the heat capacity of different materials unless their masses are known. Okay, not useful. So therefore, we have specific capacity. Let's look at this example. Specific heat capacity of water is 4200. I will show you how to annotate. Please write down C small subscript W equals to 4200 joules per kg K. You want to write degree Celsius also can, but don't forget your degree. Don't just put kgC. So what did I use? Small letter or big letter? Small. I subscript W. Why I need to subscript W? Because later on there may be specific capacity of oil. I mix these two together and have specific capacity of copper container. So this is, I consider good practice. It will help you to do your calculation much better. So it actually means 4,200 joules of energy is required to raise the temperature of 1 kg of water by 1 Kelvin. Let me ask you, how much energy is needed to raise 100 grams of water by 1 Kelvin? How much? 1 kg to raise by 1 Kelvin, I need 4200. 100 grams to raise it up by 1 Kelvin, I need 420. Get it? Then it makes sense, You go back, you cook your Maggi noodle, 100 grams of water. How much energy you need? Only 420 joules. But if you are cooking for everybody, 1 kg of water, how much energy do you need? 4200 joules per Kelvin. Have you noticed that for success criteria C, you need to apply this Q equals to MC change in theta. How many variables are there? Hey, last time I included this because this was in my previous notes. Okay. Last time we have this, or even now, O level, they still like to ask you to describe experiments. Okay. Example. Better listen, For this, how do we find the CG? Describe an experiment. Describe an experiment. I gave you all this example in your notes, right? We have to get different pivot point and then hang it. And if I hang it here, and if they cross, then this is the CG. Yes? So you must be able to describe. I have seen questions whereby they ask you to describe how do we determine specific heat capacity of a solid. Basically, this is how the scientists got the values. Okay, they conducted all this experiment and then get average and all that, making sure that it's reliable. Then they get values like 4200. Can Okay, take note, if two or more substances with different temperatures are in contact, there will be a transfer of thermal energy. Now, according to principle of conservation of energy, if there is negligible or no transfer of thermal energy to the surrounding, thermal energy transferred to one substance should be equal to the thermal energy transferred by the other object. If now these two are in contact and they transfer energy, can I say the transfer of object 1 to object 2 will be the same? Then after that, I will have M1 C1 change in theta 1 equals to M2 C2 change in theta 2. We will be using a lot of this method in solving. You know why? Because it involves transfer energy between two objects. So you have to always find what is common between these two objects. Sometimes can be mess. If you want to spend your time here talking, why do you attend my lesson? Go somewhere else, I give you permission. Or you prefer to watch my live feed, my what? Facebook what live stream live stream. Then you all can like press like, can send me gift as well, things like that. Can sell products. Okay, then Arya, you will solve C1. Later you present. Jeremiah, C2. Ara, pay attention today. So I'll get Skylar. Okay? So the rest can try now. C1, C2, C3. Huh? Finish already ChatGPT or tuition?
We did it just now.
Hey, C1, C2, C3.
24. How do you heat up a metal? That's exactly what I was just asking for. Why is it that a bigger object has more thermal energy?
There's more what?
Thermal energy.
Yeah,
What?
more particles.
So?
If you have 1 kg and 2 kg, which one has more particles?
2 kg.
2 kg. So which one have? If I ask you lah, would you rather be scalded by a 1 drop of 100 degrees water or 1 bucket?
Sure.
Why?
Because
It's
the
only
one
one
drop
drop.
covers less surface area,
No.
so it'll be less part of my skin.
That one big bucket has millions of 1 drop. And if every 1 drop carries that amount of thermal energy, wouldn't that one big bucket contain more thermal energy than one?
Okay, I understand, but how do you write it in like formal terms? Like let's say the exam asks you, why does an object with more mass have more thermal energy?
Same object.
Same material, why does more mass have more thermal energy?
Because we have more particles. Like here.
So that's literally the answer. More particles.
More particles. More energy can be stored. Correct.
But then for this question here, right?
Yeah.
It says X has more thermal
Initially,
energy than Y.
Yeah.
It's correct. Then energy is transferred from X to Y. Since X has more energy than Y, it's also correct.
But are they the same temperature? If I put that 1 drop of 100 degrees into 1 bucket, same temperature? Would there be transfer of thermal energy?
Oh, that's a trick. Wait, but I thought more energy means more temperature.
No. No. Okay, then you see that one drop and a big bucket. Which one has a higher temperature? Both 100 degrees. But which one is more energy?
The big bucket.
Yeah.
Ah.
How can?
Yes, can. Finish.
Quite simple, right? The formula one. But the MCQ requires more thinking.
I also put it instantly. I didn't give a single thought about it.
What are you doing? Hey guys, time is up. Next time, please come early for lesson. We started lesson at 15 minutes after that, you know. Take note, there's no bell, so you all have to remind your teacher to let you all go. Because prelim. So now actually I'm late by 2 minutes. So please finish up your first these 3 questions and then next lesson I'll go through.